resilience is the nature which can make a comeback. So resilience basically means to regain that powerful personality of yours after tackling some problems or after being free from some stress. So resilience and elasticity can also be related, as we know that if we put some object under stress, after removal of the stress, the body will regain its configuration. So similarly, if we suddenly put some force, try to deform it, it will just changes some shape, but it will try to regain its original configuration. So this is how we can relate elasticity with resilience. And before talking about more on this, we have to talk about work done per unit volume in the strain. Means when we are trying to change configuration of a body, shape of a body, we have to give some work. And in elasticity, when we are trying to change its shape, it will try to regain its shape after removal of the force. And while we are trying to change the shape of the object, we are doing some work. So how to calculate that work done in the body? As we know that if we are doing some work, the work done will be stored inside the body as its potential energy. So first we have to talk about longitudinal strain. So we know that gamma, Young's modulus, is equals to longitudinal stress by longitudinal strain. So we can write this as gamma equals to F by A, longitudinal stress by longitudinal strain, small l by capital L. Now from this we can find the force. Force will be equal to gamma times small l capital A by capital L. So we know that work done is equals to force into displacement, or we can say that force into change in length. So if we want to calculate the work done, we have to integrate F dot dl. Here F is this much, so we can say that, and the change in length is from 0 to L, because initially there was no deformation, no change in length, and after application of force, the change in length was smaller. So we can find it gamma L square by 2 A capital L. We have to arrange it a little bit. It will be equal to half gamma A L, A small l by capital L into small l. So this is the force, we have found it here. So now it will be equal to half into stretching force, the force with which we stretch the wire or just try to compress it into the deformation. So now we want to calculate the force, the work done per unit volume. This is the work done stored in the whole rod or whatever object we had taken. Now we want to calculate it per unit volume. So we have to obviously divide the volume here. So this will be equal to half F. Volume is the length of the rod or whatever multiplied with this cross sectional area. So we can calculate the volume. And if I divide this thing by from this, I will get F by A into small l by capital L. And here I have half stress into strain. This is the work done stored in unit volume of the body. You will see that this formula, we can obtain this formula in case of volume strain and shear strain also. So first let me erase all these things so we can talk about volume strain. So for volume strain we know about Bulk's modulus, right? So Bulk's modulus is basically pressure as we know that force will be uniform around the surface of the object, and therefore we will consider it as pressure, force per surface area divided by the strain. The change in volume let be small v and the original volume be capital V. So now we can say that the pressure will be equals to K small v by capital V. So now we have to calculate the work done, and we know that pressure into volume will be equals to the work done. So change in volume. So we can say that W equals to P del V integral of P dot dV. So now we can say that K small v by capital V dV, integrating it from 0 to V, as initially volume was there was no change in volume. It was originally a nice cube or whatever you take, and after application of pressure there was change in volume of small v due to maybe increase or decrease in pressure accordingly. We are not talking about that increased pressure Ball's law or that. We are just talking about the work done, so we have to integrate it, which will be equal to half K small v square by capital V. So now we can say that half K small v by capital V into small v. So here this thing is the pressure, so we can say that half into stress. Here the pressure is obviously the stress into change in volume, same as that of we talked in longitudinal strain. There was half into stress into change in the length, and here it is change in the volume. So now if we calculate it per unit volume, then we will obviously divide it by volume, and if here I divide volume, I will get stress into this. This will be the strain, half stress into strain, the formula of work done per unit volume, same as that of we found in longitudinal strain, and it will also be same in that of shear strain. So first let me erase all this thing. Eta relates shear strain with shear stress. So shear stress is force per unit surface area divided by the shear, which is equals to theta. So now we can calculate the force. F equals to eta a theta. So we know that area will be equal to, let us consider a cube, then the area will be L square, and here eta a square, theta will be equal to L square into theta will be equals to change in length by original length. So now we have force equals to N capital L into small l. So now to calculate the work done, we will just integrate it in similar manner. F dot dl, here change of the length is from 0 to L, or the shear while shear strain the shift is small l, so we have to calculate it for 0 to small l, and it will be equal to half eta L square. Right, so here we found that half eta L into small l. This is equals to force, so now half into force into the shift of the length, or we same as that of longitudinal strain, volume strain, half into force into that change, maybe the change in volume, or maybe the change in length, or maybe the shift. Okay, so now if I calculate it for unit volume, then I will obviously divide the volume, and volume will be equals to L cube. So here if I divide it by L cube, it will be equals to half into F by L square into small l by capital L. Here F by L square equals to F by A. We know that area equals to L square, so this will be equal to half stress into strain. Hence we can say that energy stored per unit volume work done, or strain energy, is equals to half stress into strain. So using this formula we can calculate resilience and proof. So resilience of a elastic body is to withstand some sudden shock, sudden mechanical shock, and not being deformed due to that shock, means withstanding that shock without being deformed. So we know that work done is equals to half stress into strain. Considered a situation where the body is under some stress of P, let's say pressure P, and we know that gamma equals to stress by strain, P by strain. Then strain will be equals to P times gamma, P by gamma, right? Now here the work done will be half stress P into P by gamma. And if we are calculating the total energy stored in the body, it will be equals to this thing multiplied with the volume. Then it will be equals to half P square V by gamma, right? And if I want to calculate the resilience of body per unit volume, I can simply divide it by volume and I will get P square by gamma. This is the resilience per unit volume. Means this we are actually saying that the body can withstand this amount of pressure. If the body can withstand this amount of pressure, this is the resilience per unit volume. And what is proof resilience? It says that the maximum amount of pressure, the maximum amount of stress that it can withstand. So here I have to replace the maximum amount of pressure. Let us denote with Pm. Then it will be resilience of the body, and this will be the proof resilience of the body and proof resilience of the body per unit volume. This is for today. We'll talk more about physics in upcoming videos. Thank you.